Okay, so hopefully you had a chance to get going with the practical earlier. Let me have a look. The question just come in now. Okay, so for this problem running the thing, have you compiled? So what it's saying is it cannot find the executable my code. So it's saying it can't find your executable code, my code. So the question is, in the directory that you're trying to run this from, if you have a look for that file, is it there? So if you do something like this, does it appear? And if it does, then it could well be that it's not, because you're not running in home. I assume you're not running in home. You're running in on a work file system. It's not automatically picking up the location of this file. So you just need to bind the directory you're currently in so it can find it. So say you are in a directory like this. If you're in a directory like this, what you'd do is you'd add to a singularity line, and you would add this directory as one of the bind directories under the -b flag, and then just add it onto that list of ones that are already there. Let me just copy an example. Of course, you want to change that. If you're not going to be in work TA015, TA015 Adrian J, you're going to be somewhere else. So you need to change that first directory I've listed there. You just bind that one in. The reason that this is not included in the notes is if you do it from your home directory, because home is automatically bound for this stuff, and because we're not running on the back end, then it just works automatically. But if you do it anywhere other than your home directory, then you need to add in the directory you want to use. Okay, so hopefully you had a chance to try and install some software and try and run a bit of software with containers and with parallel, well, with Python and with R on the back end, and that hopefully makes a bit of sense. It's straightforward to install things, but you need to make sure they're in the right place. Containers can be complicated, but you can generally work with them pretty well without having to do much. Then the question is, if I'm doing data science, what can I use to exploit the system to run my programs? Because the whole point of coming to a system like ARCHER2 will be that you've got some big jobs to run. You've got large amounts of data to process, large numbers of files, things that need large amounts of memory, something which means you can't run it in lots and lots of you can't run it locally on your laptop or on a desktop or even on a local university machine where you are. Here at Edinburgh, we have local parallel, small-scale parallel systems. The one in Edinburgh is called ECDF. And you get lots of people running single-core, single-node jobs on there. If you're coming up to ARCHER2, it's really designed for sort of large-scale jobs, things that need big resources, for some definition of big. And so really the question is, okay, I have my application in this example is Python. How do I use all these resources? I've got a Python thing which is very slow. How do I use larger numbers of Python processors or nodes or threads? I've got lots of files to process. How do I do that? And so if we just have a look here, what we can do in Python here, again, we're not really teaching you parallel Python. We're just saying if you can do parallel Python, how would you implement it on ARCHER2? In fact, we do have courses which teach some of the parallel Python things if you're interested in that. But if we have a look in brief at what you can do in Python, there are two, in any programming language really, we sort of have two main kinds of parallelism, or at least there's a way we can look at it where there are two main kinds of parallelism. One I would call shared memory parallelism, and this is where we use a single node but we use all the resources in that single node for an application. And this is generally based on what we call threads. So these are little workers generated by one program. And you can use all the cores on an ARCHER2 node, for instance, in all the memory. So you could have one program running that used up to 128 cores, or even up to 256 cores if you want to use those hyperthreads, and all the memory inside that node. But your program will only ever be able to use what's available inside a single compute node. The other kind of parallelism is distributed memory parallelism. This is where we configure it so that we can use multiple nodes, multiple servers at once. Obviously, that requires some communication between those servers, and this makes it a bit more of a complicated parallelization model. And so this is generally what we call a message passing approach, where you send messages between the different workers on the node and between nodes. The common programming approach or library for this is something called MPI, the message passing interface. And here, instead of running one worker, one process, and it generates lots of its own workers, we run many processes, many workers on each node, and they all communicate between each other. Now, why do I go through all this? Well, of course, Python has the same kind of approaches as well. So you've got a Python program, it's taking too long to run, you want to speed it up, you can go for parallelism. And Python lets you do different kinds of parallelism as well. So it has a threading library where you can create threads or workers from a given Python program, where you define what the threads do. So you give them some work to do, a function to run, and then you launch them and they can go off and do some work. And this is an example here. I've defined a function up here, Python function called thread function. It has some code in it here which I omitted. And then in my main program, I create 3 threads, I start them, and at the end, I wait for them to finish working. And so this is a form of this distributed memory. Sorry, completely wrong. This is a form of this shared memory parallelism. You can create workers inside a single node using this threading functionality. However, one of the issues with Python is it doesn't actually let you run these things in parallel. So Python has something called the global interpreter lock, or the GIL, and that stops you running multiple threads at the same time. So you can create lots of threads. I can create 3 threads here, and I can start them running, but any one time, only one thread will ever be running. And this is just the way Python is designed. It's because its data structures and the programs you can use are designed to be malleable. And so it protects multiple workers changing the same thing at the same time by just saying we can't run more than one thread at once. So obviously this isn't actually very useful for parallelism. It's useful for doing things like, oh, I want to handle some hardware that's going to talk to me at times I'm not sure of, or I've got some stuff going on in the background which I want to progress every so often. But if you want to run everything everywhere all at once, then this kind of parallelism, this functionality for parallelism isn't any use. Now, there is another way of doing parallelism in Python called multiprocessing. And this creates separate workers who can all run independently because they're effectively individual programs that have been created. And so this is not restricted by this global interpreter lock. We can use a multiprocessing library, and then we can create processes like we saw before with threads, and we can give them functions to run, and pass arguments in, and we start them and we join them. And this multiprocessing functionality also lets you send messages between these workers. So you can create a queue or a pipe where you can put data into the queue, and you can get data out of a queue, or put data into a pipe and get data out of a pipe. And so you can use this get with a queue, or receive and send with a put and get with a queue, or receive and send with a pipe to send data backwards and forwards. However, that multiprocess in Python is ways people can do stuff inside a single node as well. It doesn't generally, without a lot of configuration, work between nodes. And in reality, it's not designed to be high performance. So it's designed more for distributed or concurrent computing rather than parallel computing. And this is a little bit of a subtlety and sort of picking hairs, but it's designed more for independent workers who want to collaborate together in an overall framework rather than fast, high-performance communications across a large number of workers. So again, that's probably not what we want to do on something like ARCHER2 because it doesn't map onto high-performance networks. It doesn't provide high-performance, low-latency, high-bandwidth communication between workers. So we've sort of ruled out those two mechanisms for doing parallel processing on a system like ARCHER2, really, because they're not going to give us good performance. Now, there are some other things that can give us shared memory parallelism inside Python on a single node, particularly NumPy and SciPy. So these are mathematical libraries, and these actually can compile down and use the maths libraries, so things like Cray maths libraries or the Intel maths libraries, which themselves do a parallelism inside them on a single node. So you can speed up, you can do large maths calculations pretty quickly inside a single node using all 128 workers on something like an ARCHER2 node. But if you wanted to go beyond 128 workers, you'd have to do something differently. You can also use Python to interface natively with C code or Fortran code or C++ code, things like that. So you could write your parallel functionality in a different language and call it from your Python. Now you're starting to get into quite complicated approaches. And there is something called MPI for Pi, which is this MPI, this distributed memory parallelism functionality, but implemented inside Python. And we can run that on ARCHER2. So there's a direct interface to MPI from Python. And if that's something you're interested in doing, writing, full-scale parallel program in Python, then we have courses and lectures on that as well. So that's definitely possible. However, from a data science and machine learning point of view, the way people tend to do this is different. So these are the things you can do with Python, and we would avoid, the built-in stuff with Python. But you can go off to NumPy, SciPy, MPI for Pi, and get your parallelism that way. But the things that people generally do is use a different framework, and there are a few of them around, but the one we're going to look at today is Dask. And so Dask is a distributed computing framework built on top of Python. So I'll share the lecture for that. Okay, so the Dask approach is really to, and the reason we discussed this here in this course is that Dask is really quite well suited or designed for optimizing data science and data analysis style problems, because it's designed to leverage the Python libraries, which people heavily use for data science, and provide parallel functionality to that. So functionality to distribute data across multiple workers and distribute work across multiple compute resources. So Dask is a library built on top of Python to do some forms of parallel computing in Python. And actually it comes in a couple of different parts to Dask. So we have the front end bits, what we call the collections, which are the interfaces you use it from. So you can see it's got things like arrays, data frames, bags, futures, and delayed interfaces. We'll come on to those. And then there is another set of functionality which takes these, turns them into task graphs. So this is something which defines the dependencies between your operations in your program, and then schedulers, which will run it on different styles of resources. And there's a lot of documentation for Dask online. I mean, the nice thing about Dask is it's compartmentalized, so you can use different parts of it, and there are a range of different schedulers which can give you functionality that may be useful to you. So it goes everything from single node up to distributed and integrating with the batch system that we have to submit its own jobs and these kind of things. So the fundamental approach for a framework like Dask is task parallelism. So it's to split the work in a program into individual tasks which can be run separately. And then it's to schedule those tasks on available compute resources and then execute those tasks. So here's an example of a program. This is a task framework of a program that I wrote for Dask. And I can actually produce you nice visualizations like this. So it can show you what it's doing, where we have a number of inputs coming in here. So these are numbers and outputs of functions coming in here. And they're all producing results, which are then taken into a sum function to produce a final result. And so this is the task graph for Dask, and we can see the dependencies here. Everything on this level can be run separately. Everything on this level can be run separately, but the sum can't be run until all these have been completed and gathered together and produce your output. So here it could run all this bottom level in parallel on different resources, and then take the results of them and then run this sum by itself and get the result out of it. But the nice thing is that you don't have to do any of this design of the task graph yourself. You don't have to do any of the work to construct these things. It's all done for you automatically. So what does, how do you use Dask? How do you interface with Dask for your program? Well, there's three main data types you can use, which have functions built into them, which provide you this parallel functionality. And really they map to NumPy, which is the array stuff, pandas, which is the data frame stuff, and unstructured types, which is the bag stuff. So if you're doing stuff in pandas or you're doing stuff in NumPy, then there's likelihood is there'll be functionality to map that directly into Dask functionality, which can then automatically be run in parallel for you. And it comes with some nice features on top of that. So there's functionality like X arrays, which lets you do work with data which wouldn't fit in memory, and these kind of things. And what Dask does is let you to distribute this across compute nodes, across workers, across cores, but still process it as if it was a local single program running on the desktop. If you have more complex use cases which go beyond what is automatically implemented for you in Dask, then there are ways to also manually construct your own task graphs and implement those using things like the Dask delayed interface, the futures functionality, data movement functions like gather and scatter of data, and low-level coordination functionality for queues and locks and variables and these kind of things. So Dask does let you also build more complicated, more custom task graphs yourself if you want. If you're getting into this level, though, of course, it's always worth thinking, is Dask the right place to be doing this, or should I move to something like MPI for Pi and write my program that way? Okay, so what does this look like in reality? So this here is an example of doing something using Dask arrays, which, as I say, is very much like a NumPy functionality. And here you can see you can just create Dask arrays. So here we have import dask.array as DA, x equals DA, random.random, and then we create an array of 10,000 by 10,000 in chunks of 1,000 by 1,000. So this first bit here is very much like standard Python NumPy, but we've got some extra stuff here where we're telling Dask how we want it to split the data up into chunks. Okay, and so you can create random data or these kind of things. There's a whole list of ways you can do. You can bring in NumPy data directly into Dask. So here's an example where we create a NumPy array and then we create a Dask array from that. You can't do it for arbitrary NumPy arrays, so there's a restriction on the kind of NumPy arrays you can use, but in general you can do. And what Dask actually does is it uses NumPy as the lowest level data structure, and it creates multiple NumPy arrays on different workers, and then it handles the communication between them. So it should still be fast down at the NumPy level, at the chunk level, but it's handling the sending data backwards and forwards to workers, these kind of things. You can also create NumPy Dask arrays from NumPy binary files, from Z-array binary files, and load a bunch of files directly into Dask arrays, i.e. from NumPy or from Z-array. And you can concatenate and stack arrays. So you can take a bunch of separate data structures and put them together to create a Dask array. And you can create Dask arrays from other Dask functions, so a delayed function. Now, I've got a reminder here saying, remember, tasking means everything's lazy, but that doesn't actually mean anything at the moment because I have not mentioned it. But what Dask does is you tell it you want a Dask array, you give it the Dask array, and when you run your program, it goes through and constructs the task graph, which looks like this from it, and works out where all the Dask array parts need to be, when they'll be updated, etc., etc. But actually what Dask does is it constructs this whole task graph first, and then it only runs it when you actually want the data. So it does it, generally it does it in what we call a lazy format, or a lazy approach, that it doesn't run any functionality until you actually ask for the output. So you can define all the sum and all the independent things that go into it. Until you actually ask for data here, it doesn't run the overall computation as well. So that's what it means by in tasking means everything is lazy. You can create this program here. I can say X is a Dask array, but it won't actually create X until I try and use X somewhere, or I call a function on it to say, please calculate me X now. Now you can, obviously, once you've created your Dask arrays, there's a whole bunch of things you can do on it. So it supports most of the NumPy functionality, but not all of it. So arithmetic operations, it will let you do on Dask arrays, addition, subtraction, multiplication. You can do reductions across axes, so sums and means and standard deviations. And you can do things like tensor operations, matrix vector operations, slicing, and some linear algebra stuff. So SVD, triangular stuff, least squares on Dask arrays. It will automatically do these for you. There's a whole bunch of things that it doesn't do, which NumPy does do, though. So there's a bunch of linear algebra functionality which has not been implemented. You can't have as relaxed array shapes as NumPy lets you, and you can't necessarily do sorting or iterating over the arrays properly. But if you're interested, the website specifies what Dask will let you do in the NumPy array stuff. The Dask array stuff compared to NumPy array, I should say. Then you can do a whole bunch of very similar things with Dask data frames as you could do with Pandas data frames. And just like we saw with NumPy array to Dask array, in Pandas data frame to Dask data frame, really all it's doing is creating you a local Panda data frame on each worker and then connecting them together and putting the data across them. So just as before, we can create a data frame like you would a normal Pandas data frame. So from CSV, from a whole bunch of files, the formats or databases, from a Dask array or from another delayed operation and from other things like that. And then there's functionality in there to run a whole bunch of operations on it as well. So you can do the same as you could for Pandas. You can do independent operations, so element-wise, row-wise, locations of data, aggregations, etc., etc. There's a whole bunch of group bys, drop duplicates, index, resampling, compute averages, do correlations across the whole data frames, and do some kind of reordering of things. So group by set indexes and these kind of things. But you have to be slightly careful with them because you split up your data frame now across multiple workers. Doing global operations across them all can be expensive. Things like setting a new index on an unsorted column can be expensive. Group by applies or joins on unsorted columns can be expensive. And the DAS data frame doesn't do some of the more exotic data structures or data features as the Panda API. So there's a lot implemented in Pandas. DAS data frame doesn't do everything. And finally, operations are generally slow in Pandas, like iterating through a data frame row by row rather than using a built-in function that does that for you, will also be slow on something like a DAS data frame. So those are two big ones. Arrays and data frames mimic common data science data structures that are heavily used in a lot of places, and let you do parallelism on those, so you can use more than one node, more than one worker, and support larger data structures than you could fit in the memory of a single node, and these kind of things, or larger numbers of files and all these kind of things. You can also create, if you're working with data which doesn't naturally fit into an array or a data frame, there are ways to do this. So the bag will let you do a list or a set style data. So it's very much like a tuple in Python. It's immutable, but you can have an unordered collection of data with repeats. Once you create it, it's immutable, but it lets you do operations like group by, filter, fold, map, and those kind of things. So if you have unstructured data, semi-structured data, text data, log files, these kind of things, then it lets you parallelize a range of computations across those. The caveat is it's not as optimized as the rest of the stuff, so it uses multiprocessing rather than threads inside a single node, and that means there can be, the operations are slower when you're doing work in collaboration with other workers that hold part of the bag. But anyway, you can see there's a whole bunch of, you can create them from a sequence or from a range, from reading text, from a data frame, so you can create bags in a range of different ways. And then there's operations like accumulate, any, all, count, max, min, sum, these kind of things. So you can see examples here where we say B equals this from sequence 1, 2, 3, 4, 5. How many workers we want to split it over? So here's 2, and then we say an accumulate, add, and this here dot compute at the end. This forces Dask to complete the result. So it stops it being lazy and says, actually, here, give me the actual output here. And example here from sequence, true, false, all dot compute. So it is exactly the same kind of operations there. You can also work on other functionality, so build some filters. You can create a function which does a filter, and you can apply that across your whole bag, or a lambda in the same kind of way, etc., etc. You've got to remember that bags can't be changed; they're immutable. Arrays and data frames are faster, more performant than bags. So generally stay with the data frames and arrays unless your data really isn't amenable to go into one of those two formats. And the group by can be slow, and so there are ways to get around this. Fold by can be used instead of group by sometimes, and that can be useful. Okay, and as I said before, it's also possible for you to not necessarily use any of these underlying data structures from Dask, but to actually just build your own task graph and tell it what data needs to go between the different stages. And so you can do that with this what's called delay functions in Dask. So there's an example here. I've got my code here in my top left of this code blocks here, which is I've got a function increment, a function double, a function add, and you can see that sort of maps back to what I've seen before in my task graphs. And then I iterate over a list and say increment, double, add, and append it to the output. And in the end, I do a sum of all those things that have been added. So that's my original functionality. And I can turn that into a Dask delayed graph, so into a graph in two different ways. I can either use a delay function or I can annotate my code. So if I annotate my code here, I just tell Dask these functions are all delayed, and it will automatically, everywhere they use, build that into a task graph, and then I can say I want to get the sum output of the delay function and compute it here. So that's the equivalent of this over here, but that will run this in parallel where it can. Where increment, double, and append can all be done in parallel, it will do that. And you can do the same over here actually. So you don't have to decorate each function. You can just actually turn a non-decorated function into a delayed function by calling this dask.delayed down here as well. So you don't have to make all versions of your function tasks that are running parallel. You can just do it in the places you want to do that. So again, notice we're calling this compute function at the end to actually make sure the task graph is actually calculated and run in the end, not just constructed. But there I can do arbitrary things here. I've not had to use a data frame or an array or a bag. I've just got functions which are getting data passed through them, and it will do the other functionality. And futures let you do this, but even in an even more complex way. So futures let you build completely arbitrary task graphs. Similar to delayed, but tasks execute as soon as they're available, and you can do more complicated things inside them. So here's an example of my functionality again. I am creating a client, a futures client, and I'm submitting these three functions to run. I'm getting the results from it, and then I'm doing some more work on it here. So I can see I can build arbitrary task graphs this way with much more control over what's going on. However, once you get down to this level, or even indeed this level, you're sort of heavily into the tasking side of Dask, and it's not really where we point most people. Most people it's useful because you can map your standard functionality, your NumPy arrays or your Panda data frames into Dask and not have to worry about how all that is put together, what runs after, before and after what, etc., etc. It's just all flows for you. So I would, but Dask does allow you functionality for things like building your own task graphs, but it's probably not the place you want to start. Okay, and so that's really on the building the task graph side, so the interface and the building the task graph side, but none of that really addresses how you run the functionality, how you schedule and run the tasks once they've been constructed. And here's an example where we're starting to see that kind of come in here. So here we're creating a client, and we can say whether we want it to be threads or processors. So Dask has a bunch of schedulers and execution functionality that it uses in the back end to start things up. By default, Dask, you generally get defaults to threaded parallelization, single node, maximum calls available, and But for Dask array and Dask data frame, that's what it'll do if you don't tell it to do anything else. The bag doesn't use threading. And when I say threading here, this is not the same threading which is restricted to the global interpreter lock in Python, so it can all run in parallel. It maps down onto C or C threads, something like OpenMP under the hood, but that will let you exploit the parallel resources on a single node. The exception is bag functionality, which doesn't use threads, it uses multiprocessing. And again, it can use all the workers on a single node, but it tends to be a bit slow because it's using this slow multiprocessing functionality. And that's because processors are heavyweight, you know, they've got more overheads associated with them. They're more functional, but they've got more overheads associated with them. But you can then change what Dask does. You can do things to decide how your Dask will execute things, and actually also go to more than one node to scale up to multiple nodes, which is of course what we want to do for a system like Archer. So you can modify how it chooses to schedule and run things in your program and your functionality. So for example here, the default scheduler is usually threading, but you can change it to processes. As you can see up here, we've got this default scheduler threading, which works well for arrays, data frames, and delayed. But if you've got native code that you're trying to parallelize with this, then it will be restricted by the GIL, and you can get around that by changing it to processes. But you can do more advanced things. So you can create a client, and the client can be used to schedule jobs on other things like that, so single node or multi-node, asynchronously, etc., etc. So this all comes from this Dask distributed extension to Dask, which you may have to install, and that's part of the third practical is installing that. And that gives you both single node and multi-node functionality. It has the Futures API, a dashboard, and can improve some data functionality as well here. So some examples on the top here, sorry, on the right-hand side here, of the kind of dashboard showing the task screen and the scheduling from a Dask program running on a system like ARCHER2, where we can see, let us see what tasks are running, how many workers are being used, how much memory is being used, and those kind of things, which can be quite nice. So you can do custom, when we've got this kind of scheduling options, we can do custom resources and schedulers on a per run basis and with a context. So we can specify for individual compute parts of a Dask, where we call compute exactly what schedule we want to use there. Or we can set up a configuration for the whole program, or we can use that context. So here, this is a configuration for the whole program. Here we are specifying within this context, so we've got a with, and anything computed indented from this with, we'll use that context. And we can do more fine-grained control as well. So we can actually set up, actually, I want to use 8 workers, I want to use 8 threads, I want to use 8 workers, or 4 workers down here. And there's a whole bunch of different functionality here that we can use to specify how exactly we want to run things on a single node, across nodes, or even into batch systems. So it's possible to get Dask to submit jobs to a batch system for you as well. And so these are all different batch system implementations. The one, of course, we're interested down here is the Slurm cluster, and there is one that works for the ARCHER2 Slurm system where Dask can submit jobs as required into that. It's also possible, there's a Dask MPI extension which lets you use MPI to run the jobs and schedule the jobs, which lets you run a job using the MPI wrapper, and then it will implement and interface with that, with all the workers that have been spawned as part of this MPI program, and use those available resources as well. So that can be a useful one on a system like ARCHER2. So we'll have a look at in a minute at some specifics of how we use this on ARCHER2, but it's just to show you that there is a range of scheduling and execution functionality which can map to different systems as well. So if you want to use it locally, then Dask will run quite fine on your laptop, but you can also scale up to these larger systems on different resources. There are some guiding principles here, of course, when we're using something like Dask. It's additional functionality. It has some costs associated with it, some overheads, runtime costs. So it can make your program slower if you don't need it. So the idea is, if you don't need Dask, if you're not running out of time, if you're not running out of memory, if you're not wanting to schedule complex things, then you shouldn't use Dask. So NumPy arrays, Panda data frames are generally all faster for small scale in-memory functionality. Dask is important when we get up to things that are taking far too long in a single node or don't fit inside a single node. And then we want to use multiple nodes at once. To get good performance, the size of chunks you use with something like a data frame or an array is important as well. So too big chunks, you don't get enough parallelism. Too small chunks, there's a larger overhead with distributing the tasks, and that can cost you performance as well. So that needs a little bit of tuning from your program point of view on a given platform. Compute should be called as infrequently as possible. So forcing the task graph to be evaluated should be done as infrequently as possible, because the task graph it can do some optimizations if it can see the whole task graph before it runs. So it can find out intermediate results are not needed and get rid of those and those kind of things. But there are times when actually you may need to run the compute multiple times and at different stages in your program if the task graph gets too big. And if we're going up to large scale parallelism, so we're running on lots of nodes with lots of workers, there's often good scope for mixing workers and processes. So mixing threads and processes in the same Dask parallelism will give us some performance benefits. If you're just doing small scale parallelism inside a single node, then the threads will work well. It's useful to load data with Dask. What does this mean? Well, this means rather than loading it into Panda data frame, then setting up Dask from that Panda data frame, rather than loading it into a NumPy array and then setting up the Dask array from that NumPy array, loading it directly into a Dask array or a Dask data frame can give us some benefits, both because Dask tends to support out-of-memory operations, i.e. it can create data frames or arrays that are bigger than the memory you have available to you, and because it lets you distribute that data straight away. Finally, what they suggest is that you don't save data in its largest form if possible. So persisting of data to memory when the data is being reduced is probably a sensible thing to do. So you don't need to store the whole data frame. You can store the actual results you need from it. You don't need to store the whole array. You can store the actual results you need from it. Okay, so Dask is available on ARCHER2 as part of the Cray Python package already installed. We've seen a little bit of this already. By default, it's plain Dask, so it only has the threaded and shared memory backend. It doesn't have the distributed and the job queue and the MPI stuff installed. So to do things outside a single node, we want to be able to install the distributed and the job queue stuff. And the way to do that is shown here on the slides. Now, this first line, install Dask distributed, we've already seen today, and actually there's some issues with the current version of Cray Python on ARCHER2, and it may be worth actually doing a load of a slightly newer version of that to get around those issues. So let me just see if I can correct this whilst we're here to make it more apparent what is being asked for. Here we go. Yeah. So if you load this CreaPython 3971, that should let you then install these things here without having to, without complaining about a mismatch between things. When we go into run a distributed job or something like that, currently we need to submit that from the compute node. So we need to do an interactive job to submit it. And that's because Dask does this thing where it needs a connection from the controller, the Dask controller, to its workers to do a scheduling. And it's possible to set that up on the login nodes and get that connecting through to the compute nodes, but it's a bit tricky. So we just use an interactive job to submit our run and do it that way. If we're just wanting the threaded Dask, the single node stuff, then we can just run our program as normal. As long as we've got our process binding and thread placement sensible here with our super use per task and a task per node for what we want, then that will just run Dask sensibly, and we can do that in an interactive manner as well. But if we want to do something more complicated, something where Dask can submit jobs to the queue for us, and will manage those jobs for us and all these kind of things, then we can use this Dask job queue Slurm cluster functionality. And so here's an example. This is inside a Python program. I define a cluster. I tell it about, each node has 128 cores. You can run 128 processes. The things it needs to add in to run, things like a project, you'd have to change that to TA 105. How long jobs need to run for, your Python user base, these kind of things down here. And then once you have that, you can then set up a cluster inside your program that says, run 2 jobs, create a client, and then once you set that client up, this will connect your 2 nodes together, and then Dask just uses that when you go off to do your compute here. And so that will let you run much larger jobs on something like ARCHER2. So you can create arbitrary job size things here, which will be able to process very large Dask arrays or Panda data frames or these kind of functionality using this here, this job queue idea on ARCHER2. But as I say, if you have things where you just want to parallelize inside a single node, you just need up to 128 workers, then you don't need to go to that level of complexity, and you can run Dask in a program like this. You won't get the nice front-end graphical interface stuff in the same way, but it will still run the programs in parallel and give you sensible performance. Okay. Any questions about Dask? That's good. If there's no questions, then we can just go. We're slightly early. That's always a good place to be. We can go on to the practicals. So if you've not quite managed to finish the containers practical, then just go back and have a look at that one again. Let me have a share of that again. So this is the containers practical. But if you're happy, you're done with that, you've got no questions on that, then there is a set of practicals to use Dask on ARCHER2 from the standard Dask arrays and the Dask data frames, all the way up to creating that kind of application example I showed you, through to more functional ones where we do a Mandelbrot calculation or a pi calculation, and trying that out on ARCHER2. So have a go, have a see if you can get through them. If not, there are actually example solutions in there as well, if that's useful to you. But please do have a go and let me know if there's any questions. And what we're going to do, timetable now is from now until 3:30. Then we have a break, and then we start the last lecture at 4, where we'll talk about it's scheduled 4 till 5. The lecture won't take an hour. And there's a similar set of exercises to try out with R on ARCHER2 as well. And so I appreciate most people are either interested in one or the other, but most people are interested in both Python and R. So apologies if R was the thing you're here for and we've done all Python first, or vice versa. But as I say, this functionality is generally quite useful for data scientists who tend to go across Python and R, and so that's why we combined them, the two of them together into this course. Of course, there are other things you can do and maybe of interest, but that's what we're focusing on here. So give the exercise with Dask a go, and we will be around to get your questions, solve any problems, and give advice you need. If you also have your own Python programs you want to try out on ARCHER2, please also feel free to do that. And if you have any questions about those, I'm more than happy to have a look and answer those as well. And then, as I say, we'll come back at 4 for the final lecture and exercise on R. Okay, let's get back going again. So we've covered the Python side. Now I'm going to look at R and do an equivalent thing for R. So what R's installed on the system, how do you use R on ARCHER2, and how can you do some of the parallel functionality with R. And I should say up front, there's quite a lot of different ways of doing parallel functionality with R. We'll just introduce some of them and discuss how they get used or implemented on ARCHER2. Again, we're not really looking to show you exactly how to do data analytics at scale with R. If you're interested in that, do get in touch. This is more assuming you know how to use R, what are the different ways we can exploit this on the system. So as with Python, as with any applications, any parallel program approaches, there are different ways and different motivations for wanting to parallelize an R application. It may be that the program takes too long. It may be that the program's quick, but you've got too much data to process. So that could be lots and lots of files, lots and lots of data sets, however they're stored. And it could be that an individual data set is too big to process in a single place on a single node. So you want to split it up so you can fit it into memory on multiple nodes. And of course, on ARCHER2, most nodes have 256 gigabytes of memory, but we have the large memory nodes as well with 512. So if it was just a question of staying within the 512 gigabytes of memory, you could look at ensuring that you just run on the large memory nodes and get around it that way. But at some point, generally, if you've got a application which is pushing the limits of what you can complete on a single node, you're going to want to be able to split it up and parallelize across a range of resources to either speed up the runtime overall and get better performance, or to fit in memory, these kind of things. Now, there's a lot of different ways of doing this in R, as I said. If you have a look on the CRAN website, there's a high performance computing page with lots of different versions of doing parallelism. And so we can look a bit like we can do with Python at both implicit and explicit parallelism, integration with a batch system, distributed computing, and big memory and native code interfaces. So we didn't really talk about implicit and explicit parallelism directly when we're talking about Python, but implicit parallelism is the kind of thing that you get. We mentioned in the Python examples where part of a library has some parallel functionality built into it, which you automatically get. So something like NumPy, you already have a compilation down to something which uses threads and can automatically use the cause in a node for you. That's implicit parallelism. Whereas explicit parallelism is more the Dask, the MPI, these kind of styles where you write the code, you add in specific things to use parallel functions, parallel approaches. And just as we saw But Dask gives us the option to integrate into a Slurm batch system to submit our own jobs and these kind of things. R also has functionality which can integrate into a batch system, integrate into Slurm, and submit jobs as well. So we should just go through these in a little bit of more detail. So this is now no longer implicit, but explicit parallelism. We're going to have a look at some of the shared memory approaches, so things that could use a single node. And there are ways we can do that depending on how our code is structured. If we have trivial parallelism or embarrassing parallelism, this is basically running exactly the same thing but just on a different data set. Then we can use apply or map functions to do that. If we have loops where we're looping through, say, an array or a matrix, then there's for each that will do that. And then there is threaded functionality, which lets us do more complicated things, create a different function for each worker, those kind of things. And then if we look at distributed memory parallelism, where we're going to go across compute nodes, where we're going to use more than one compute node at once, then we can use something like the parallel library in R, the Snow library. There is an R MPI, just like there's an MPI for Python, and then for each and other things as well. But if we go and look at our implicit parallelism to start with, or we could call that automatic parallelism, then there are a bunch of things that are already built in there. So just like NumPy will automatically parallelize things for you if it's compiled down to a maths library like MKL or CreaLibSci, that does that for you automatically. The BLAS libraries can be used to give you shared memory parallelism. So if you have a look at this kind of functionality here, we've got a matrix A of a certain size and matrix B of a certain size, and we do an operation on those two matrices to produce a matrix C. We can use something like that to get parallel performance using something like the data table library. So if we, so this top one here should automatically give us some parallelism, and the data table library, if you import it, you'll see it has some similar kind of things built into it. So in this example, if I import it on Archer by default, it will try and use all 128 cores on a node. And so it will give us that functionality. Of course, we can control this because by default, you want to use all 128 workers, but that may not be what you want to run. You may want to run a number of our programs on the same node, each using 8 cores or 16 cores. And so you can control that using this OpenMP number of threads variable here. It's an environment variable, so you can do export OMP num threads equals 2. And then if you did that before you ran R, when you ran R and imported this library, that data table, you would get two workers, 2 threads instead of 128 threads. So we have this similar, that's exactly the same for NumPy in Python and SciPy in Python as well. If you set the OpenMP variables before you run your Python program, you will generally only get that number of workers. So it's worth looking out for. There's a bunch of functions or underlying operations that have parallelism built in, will automatically exploit multiple workers inside a single compute node. If we have a look at what we would call, I shall say, trivial parallelism. So trivial just means we don't have to do any specific engineering or changes or modifications of that code to work in parallel. Really, here we just want to run the same code as we had before, but on multiple different inputs. And those inputs could be files, or they could be generated data or something like that. So the same code executed independently, maybe with different initial conditions or maybe with different data sets. And we can have a Slurm job array to support this, like we saw in one of the earlier lectures. And inside our individual programs, we could, if we passed in the Slurm job array ID, we could then read that inside our program here as an argument, use that to set the seed for our random number generator, reading the same data set, and then run a k-means analysis. And if we run many of these with different seeds, we should be able to sample our data space nicely. And that would, here's an example of running that. Here I'm manually passing in that seed of 1 here, and it'll produce the output here, data. But I could run that as a job array and replace 1 here by the slurm job array environment variable, and the same on this here, and that would produce me as many files, all with different data generated from different random number generator seeds as I was running array jobs. We'll quite often call this a task farm, or it's a very simple task farm, but it's this idea of just running the same thing on many workers, but with different data sets or in initial conditions. If we go a little bit more complicated than that and make some modifications from our code, but still trivial parallelism, we're not having to do any particular processing of results or in parallel or anything like that. We're still running everything in parallel. We just want to do that inside the program rather than as a job array function. We can use functionalities to split, apply, and then combine data, which is built into some of the language we have, some of the libraries we have in R. And so we can split up data, which does the partitioning of our data into multiple groups to be worked on. We can apply operations to each group, and then we can combine results at the end here. So an example I've got down here, this is the serial code. I read some data in, I run the k-means analysis on that data, and I print out the results. And this will just use 1 worker. If I want to parallelize this across 4 workers, then I may need to make this a little bit more complicated. I want to make this something where I can actually split up my k-means into multiple k-means, each with a different starting point, and then use a supply function to split up our data. So we're applying 25, 25, 25, and 25 to this function. So this will give me 4 data sets, each start with an end start of 25, number to start on, 25. And that will create me an array of results, which I can then apply using this thing called sapply to sum up the results from those and then gather that data together at the end. Okay, so you can see here we've gone from a program which was pretty simple to something that's more complicated, so we can split it up and use it across multiple workers. But there's not much parallelism going on here other than splitting our data set into chunks and then running those chunks on multiple workers and then gathering the results back up together. So it's still quite a trivial parallelism. We've not got anything complex going on here. We've defined one way of splitting everything up, but we're running the same thing still everywhere. And then once we've finished it, we just gather the data back together again. Now, of course, there are different ways of combining data together. So we can create a list of answers. So an example here is we're going to do an lapply of a function which does a square root of 2 numbers times together. And when we run that, that will actually produce a list of answers, so a list and list of answers. And so that means we may have to do some processing of our results after this to strip out the data into a single vector of results. So all I've done is taken my result and done this call of this C function to take the columns out, and I've collected together the data instead of being nested inside these multiple lists. We've got a single vector or array of data there. So that's something you've got to keep an eye on as well. Going slightly beyond this, so we can start then in this function here, where what we've done is we've split these things up, but we're not really doing very much in terms of telling it how to run these things in parallel. But there are some libraries above this which let us do control a bit more how we're doing that functionality, how we're doing that parallelization. So by default, this sapply, lapply stuff will use threads to do this. If we want to go up and use processes instead of threads, then we can use mcapply, and that will do the same thing, but we'll run it on processes rather than threads. And then we're not going to control the number of workers with OMP num threads. We control it with this environment variable here called mccores. Or we can pass that into the function directly and say, apply this on 16 cores, and it'll go away and do that. And mcapply, so multi-core lapply, will take a number of different functions or arguments or parameters to specify how things are done. So things like, can you you don't have to run all the tasks at once. You can run them in an iterative fashion and load balance across the workers we're providing, those kind of things. So it's quite functional like that. There's also a collect functionality. So this is very similar to the results collection of a vector that we have there, but this will do the parallelism and split the data up and then collect the results together again here. So here we have we're using now MC parallel, so multi-core parallel, not just to do a left apply, but to do a more functional thing. So we can do a wider range of functions with this MC parallel, MC collect. And so here's an example here where we create two arrays or lists and then collect them together into a result. And we can do that in parallel. But in more a functional approach, something more useful, we can read some data in, then we can sort that data in parallel, and we can calculate the median of that data in parallel, and we can do both these things at the same time, and then just collect the results together in a list where we interleave the data so their median and planes are put together. And so this can allow us to process very large data sets and do different things to the data sets at the same time. As already mentioned, that's, of course, if we've got things where we want to do an iterate over a loop to do different things, and this is quite common if you want to loop over a vector or a list and do things to them. Then we can also use this for each library here. So here's a re-implementation of doing my k-means in parallel, using for each instead of lapply. And here, so we have a for each. We specified a range of our loop, and we say do, and then it will do each one of these calls for each one of the iterations of that loop. And again, we're collecting into a results left vector where we want to gather all that data together and produce it. So here, all we've changed in the middle here is instead of doing this lapply, we're now using a for each do. It's also possible to combine that together into a sort of single line. Now this here, again, is not necessarily doing anything in parallel, but you can then modify this using the do MC, so to do a parallel functionality here. And when you start specifying things like that, you can then do your parallel, all these things at once at the same time. If we want to then do the same thing, but go beyond a single node, so we don't want to just be restricted to all the cores in one node on ARCHER2. We want to be able to split up and run across 10 nodes or 100 nodes because we've got a very large data set. Then we can use a number of different ways, but the example we have here is how you can use the Snow library. So if you install that, you'd need to install it, and we give you information on how to do that in the practicals. But then you can create a parallel cluster based on an MPI job, and you can then do this par lapply, which will apply to that parallel cluster because you've got this cluster here, and it will do its results. So basically here, again, it looks very similar. We have function we want to run, we've got a data set. We create a parallel cluster to say this is all the workers we're going to use. And this example here is going to take it from how you run your job. We'll see that in a little bit. We export our data, so we actually say take this data and split it up across the cluster once we've got it here, so it's ready when we run our parallel function. And then once we've done that, we can get the data back and stop the cluster and finish the program. Snow lets us do similar kind of things with parallel cluster. So we had do par before, and we were just using the Snow library for each library for the do par before or the do MC. We can also use Snow or do Snow to do the same thing across a cluster again here. So we can now split up this loop. We've exported our data, and we can run that across the cluster as well. So it really depends on the functionality you've got in your R program as to how you'd specifically want to split it up and what you'd specifically want to use. But there are different ways of doing this, and we can do it inside a single node, or we can do it across multiple nodes as well. And so that gives us lots of functionality there. We can also do similar things by doing more complicated functionality using this kind of thing. So we can get a cluster from here, and we can have a look inside our parallel machine to see what's going on, what are our nodes that we're running on, what are our machines, and we can print that kind of stuff out. And then what we can do is use this function called cluster call to run this arbitrary function on all the elements in the cluster and print that kind out. So we don't have to restrict ourselves necessarily to loops or L applies or S applies or those kind of standard functions inside. What we can do is write more complex functions that we can ship across to different workers. And we can, with this kind of functionality cluster export, we can also ship data backwards and forwards as well. So we can create cluster calls and cluster exports to move data and move work around the workers we have. Of course, that all assumes you have all the libraries installed that have been demonstrated, and some of these come by default, but Snow and RMPI and these kind of things are not necessarily there. So we have to do a modified install to install some of these things we want to use on the system. And basically that involves setting up our preferences, which I discussed a little bit earlier in the day, where we create a preference directory, create a file in there and tell it what compilers to use. Then we make sure we load the correct things, so create this programming environment, export our rlib user to tell it where to install things. Obviously this is different for each user. And then we can run this command here, our command install. We've already downloaded a version of RMPI for you, and that will install it on the Cray system here. And once that's there, you can then install the Snow package directly with R like this, and that gets you set up to use this on ARCHER2. And then once we have that built, then we can just run our Snow job as a standard batch system job here, using something like this. We've got a standard batch system. We've configured how many nodes and how many tasks we want. We load the Cray R module. We set up our rlib and our paths, and then we can just do this here. So we have a simple parallel Snow program here. We srun and we use this RMPI Snow program to read that and run the program for us. It's also then possible to build more complicated functionality again on top of that. So you can specify, here's a more complicated Snow program where we're reading in how many workers we have, and max is coming in from the environment and saying how many Slurm processors we've created. We can create a cluster, write a function which will do some work on that cluster, export some data across that cluster, and then we can do this cluster apply using the cluster environment, the size of the number of workers we want, and the function we want to operate on, do some work, get the data back, and stop the cluster as well. So we can see we can build quite complicated R functionality inside this parallel thing, which will automatically get mapped out to workers on the system here. And this is again another example of how I would run that exact program here. So as I said, this lecture wouldn't take the full hour, so we've got through it pretty quickly. But basically, the good thing about that is it gives you time to play on the system, to take some of our examples and try them out and see how well they work and what the different trade-offs with them are, and what the different implementations are like. But basically, you know, we have R available and optimized on ARCHER2. Just like with Python, we probably want to control the placement of our workers through the batch scripts and the number of threads or workers we're going to use, using things like OMP num threads or MC proc or something like that. And then there are different ways to map your R functionality into something which will work across the system, depending on exactly what kind of functions or what kind of language features you're using inside the R program itself. And there'll be, you know, a bit more advanced work you can do there to make sure that all the data is set up in the right way. You're not wasting time moving data backwards and forwards too much and these kind of things. But it's all possible to take either a group of small R programs and run many copies of them on the system, or to take one big R program and make it much faster by using multiple nodes on ARCHER2. Any questions? If not, now is a good time for me just to give an overall summary of where we're at with the course, the lecture material, because that was my last lecture with significant content in it. And just to remind you about the feedback form that we have for the course as well. And then what you can do is go on and do either finish off the Python practicals if you and the Dask stuff if you've not already done that, or to go on and then to go on to the R stuff, because there's a bunch of R exercises you can try it on the system, try running R, parallelizing at different scales and these kind of things. So just as a reminder, ARCHER2 is a big high performance computing, potentially a very significant resource for data scientists to exploit. It's primarily there and designed for people running large computational simulation things, so large applications with lots of workers working on a single program, but you can exploit it for other things. If you've got very large numbers of data files to process, you can do that there. If you've got very large amounts of data to analyze, it's possible to write R or Python programs to do that and still use a system like ARCHER2. What we try to encourage is making sure that you do that in the most optimized way possible. So using the central installs of Python and R, using containers if you're having to port complicated code across to ARCHER2, and then making sure your placement and your compilation and things are all as efficient as possible. And of course, if you want any help with that, and if you need any help with that, then it's useful to come and speak to us and see, come talk to the help desk, come and talk to people like me. If you have specific use cases, specific needs, or you're not quite sure you're doing things right. And in that way, hopefully you should be able to both exploit a system like ARCHER2 for data science, but also do it efficiently and make sure that we are using the resource in the best way possible. As a final reminder, and you'll get an email about this as well, there is a feedback page for this course, which is very useful for us to have your feedback. It's a pretty simple page. It may not be open yet. I'll just check. Let me just check whether it's open. But as I say, Claire will send you an email at some point. Yeah, it is open. So I'll just give you an idea of what that looks like, because it is as mentioned before, useful to us to get people's feedback on the training and what's good and what's bad. So the course feedback looks like this. You can actually select many courses to give feedback on, but obviously best to do when you've actually done. And then what we really want is, how would I rate this course from excellent to very bad? And you can give more detailed feedback if you want. But what the only required question is this one at the top here, the ratings, and then if there's things that are you think were good, or things that could be improved, or things that didn't work very well, or things that worked amazingly, then you can tell us more about that in there. So if you have a moment to do that once you've finished all the practical exercise and things like that, that would be useful. But otherwise, the thing to do now is to go back and have a look at the exercises, and particularly we're now moving on to, if you've finished the Dask ones, the Python Dask stuff, and there's a few bit of things to do there, then go and have a look at the R functionality, practical, this one here on R, and it tells you how to do some of the things we've talked about in the notes. Have a look, you can have a look at your usage and see how much resources you're using, and then we can do some more complicated functionality, have a look at some of the loops and the functions, and do some of the distributed memory parallelism as well. So it's worth having a look at if R is something you're going to use or something you have used in the past. Any questions? If not, I mean, I'll be around for a while. If you want to sign off and go and do your practical 0 time, and then drop me an email if you've got any problems, that's fine. Otherwise, I'm quite happy to, for you to ask questions here. I'll be around and monitoring the chat. Yeah, if you're happy to get going with the practicals, let us know if there's any problems. Thanks for coming along to the course in general.